Good morning, everyone. So let us get started with taking a look at a quick problem. So in the warm-up problem here, what we have is we have a mass hanging from a ceiling or a table or whatever, and it's hanging via a cable or cables. And so our goal here is to figure out the force of tension in each cable. So what this means is I want you to find the force of tension in the cable and in the in part A, and then I want you to find the force of tension in each cable in part B. Well, not part B, picture B. Well, setup B. B. Um, so find the force of tension in each cable for A and for B. Part A has one cable and part B has two cables. So for those of you just joining us, what we want to do is we want to find the force of tension in each cable. So there are two setups, I guess. Setup one is hanging from one cable and setup two is hanging from two cables. So find the force of tension in the cable and cable part A, setup one, and then find the force of tension of each of the two cables in setup B. Let's take another minute or two. Whenever you're ready, feel free to let me know what you found for the force of tension in each cable. Um, is it just me or is the chat button gone today?
Yeah, I don't think the chat is enabled.
I do not know what happened. I literally have not made any changes to anything. Okay, so let's just assume that all of you, I don't know what happened. I will try to figure it out, I guess. Okay, well, anyways, okay, so luckily this one isn't too hard. So I'll just quickly go through it right now. And then we'll sort that fiasco out later on. Yes, I was sort of wondering why I wasn't getting any messages or anything. And then I sort of realized that the chat was gone. That's not ideal. We'll figure it out. Okay, so we got two setups here. We got setup one, which is like this. Now we have setup two. Well, E is like this. So for setup one, if we were, let's call this A and B. So for setup A, what we have is we have an object hanging from the ceiling. So if we were to draw a free body diagram here, we have the force of gravity pointing down, and then we have only one of the force, and that's the force of tension pointing up. So the force of gravity is pulling this down with a force of 50 newtons. So in order to pull the mass up, the force of tension has to be equal to the force of gravity here. Because the mass is not accelerated up or down. So since for A, since the force of gravity is pulling it down with a force of 50 newtons, the force of tension is pulling it up with a force of 50 newtons as well. So that's just a very quick way of doing it. I didn't want to do it the long way just because I'm sure that this is too crazy. The second one, it's going to be similar, except this time instead of one force of tension going up, we have two forces of tension going up. And these two forces of tension are kind of equal to each other because these two cables are identical and they're not pointing at angles or anything. And so two forces of tension is going to be ahead. So what it means is that the force of gravity, which is 50 Newton, is 50 newtons, is going to get split evenly between each one of these cables. And so the force of tension in any one of these cables is going to be 25. So that's just pretty much it for nothing crazy. I think the general trend is that when you have more than one cable, the force of tension is going to get split between the number of cables available. Now, generally, if things are at the same angle or if they are not at angles at all, the force of tensions are pretty much going to be the same. However, if they are at different angles, you will find that the force of tension will not be the same. So that is pretty much it for the warm-up question. If you have any questions about it, let me know. I'll have to try to fix the chat in a second as well. Okay, so also the slides disappeared. Give me a second. There we go. Okay. So, what are we doing today? So we're going to quickly wrap up. We're not going to quickly. We're going to wrap up our introduction to pulleys and forces in equilibrium. So we're going to go through a few more warmer problems because I know that we like to get some practice in. So I'm going to go over a few more warmer problems and then we are going to start the main assignment, which I have called Car Alert. Yeah, so that's what we're going to be doing today. So what we're going to do right now is we are going to explore what happens with two forces of when we have two cables pointing at angles holding a mass up. So in this example here, we have a mass being hung from two poles essentially, and the cables are both at 30-degree angles relative to the mass. The mass has a mass of 50 kilograms, and so what we want to find the force of tension in each one of these cables. Once you're able to do that, I just want you to quickly think about what happens if the tension in the cables, how the tension in the cables might change if the angle gets reduced to 5 degrees. And then I also want you to think about whether or not it's possible for the cables to be exactly horizontal. But for now, let's see if we can start with finding the tension in each cable while I try to figure out what's going on with the chat. Oh yeah. So I did not disable the chat on purpose. I think some sort of setting got changed. I think I fixed it, but I think what happened in order to make the change stick or in order to make the change reflect, I think I have to restart the meeting. And I don't really want to do that right now. So for now, we'll just assume that we'll just play it by ear, I guess. But I know I did not disable the chat by purpose. In fact, it's too much work for me to do that, so I didn't do that. I don't know what happened. And before you start saying some stuff like some boomer says, before you start saying something like okay boomer, before you start judging me for my technological literacy, I just want you to know that I literally did not make any changes to any of the meeting at all. So I'm actually very curious as to what happened.
You got
Very-
hacked.
That'd be really funny. Yeah, that'd be really funny. I'd give them. I would respect them for that. So despite the fact that the chat is disabled, some of you have still found ways of roasting me for my technological abilities. So I appreciate that you are all being so clever with finding ways to bully me into quitting teaching. Okay, so I think that was hopefully enough time. Do we need more time for this? Because we don't have the chat, now I have to really use my judgment here. I'm going to start going over this if that's okay. If you feel like you need a bit more time, just let me know. Okay, so let's go through this really quickly. Well, okay. So I think we did something a little bit, I think we actually did something, a problem pretty much identical to this last time. But this time we have numbers here. So I think that it'll just be a little bit good practice. And I think the setup is a little bit different. It's a little bit different, but the general idea is the same. You have two cables essentially pulling a mass up. And this time the cables are at a 30-degree angle here. And our goal here is to figure out what are the forces of tension in each cable. Okay, so to start off, let's just start off with a free body diagram as usual. So we have the force of gravity going down. Nothing crazy. And to go up, we have two different cables. We have tension 1. Let's call this tension 1. And then we have a second one. So these two tensions, yeah, so we have tension 1 and tension 2. So because the two angles are identical, the two tensions will be the same. But instead of just trusting me on this, I'd rather show you why these two tensions. Because I know it's not necessarily intuitive to know that. So it's okay. We'll work it out. So this is your free body. This is our free body diagram here. I think that in itself is nothing crazy. But however, what we do need to do is we need to break down these two diagonal forces into parallel. So this is where we're going to use our trigonometry skills. So what we have is we have a diagonal force of tension. And what we want to do is we want to break this down into a horizontal force essentially and a vertical force. Basically, what we're trying to do is we want to figure out how much of this tension force is being used to push the object horizontally, or pull the object horizontally, and how much of it is being used to pull the object up vertically. And essentially, this diagonal force is doing two different things. It's pulling it both horizontally and vertically. And we want to figure out how much of it is being used to pull horizontally and how much of it is being used to pull the object vertically. Okay, so let's do a little bit of trigonometry here. So what we have is tension 1 is our hypotenuse, and we have our angle here, which is 30 degrees. And we want to figure out what this y force is. So this is where we're going to use our cosines and sines. So the cosine of this angle of 30 degrees is going to equal the adjacent, which is x, over the hypotenuse, which is our tension. So what we're going to do is now we're going to rearrange this so that our x force is going to equal our tension 1. We're doing something similar for our y force. So the sine of this angle is the opposite of the hypotenuse. So our opposite of our hypotenuse, y over 2, tension 1. And so if we rearrange this a little bit, we'll get is our y force is going to equal tension. So by doing this, we now have figured out essentially how much of this force is being used to pull the object horizontally and how much of it is being used to pull the object vertically. And so we can also do this for the second tension force, which is this way. But the general principle for this is going to be the same. So I'm not going to do, I'm just going to break it down now. So instead of having these two diagonal forces, what we can actually do is we can do a horizontal and vertical force for each one of these diagonal, for each one of these cables. So the horizontal force, as we found, is our tension times cosine 30. And then our vertical force is tension times sine 30. So now we turn these two diagonal cables into horizontal and vertical forces. And so now this is solvable. So while this is a little bit messy because we have a lot of different forces here, right? We've done stuff like this before where we've had everything. Okay, so now let's take a look at what we're now going to do is we are now going to solve things in the parallel and the perpendicular direction. So what I mean is basically a horizontal and vertical. We're going to solve for our forces in a horizontal direction, and then we're going to solve for our forces in the vertical direction. So we're first going to start with the horizontal direction because we only have two forces. So it just makes sense to start in the horizontal direction. So the sum of all forces. Okay, so before I start going through that, let's first examine this problem. We have a mass hanging from two poles. The mass is not moving, it's just hanging for there's two poles. So because it's just hanging, it's not moving, it's not going to be accelerating. It's not going right, it's not going left, so there's no acceleration, which means that there has to be no overall force in the horizontal direction. It's not going anywhere. So what that means is that the sum of all forces, when we combine all the forces in the horizontal direction, this is going to equal 0 because there's no overall force holding on the object. Another way of thinking about it is that this object is in static equilibrium because it's not really changing, it's not moving. So, and when something is in equilibrium, it means that the net force is going to be 0. What we have our net force in the horizontal direction is going to equal 0. What forces do we have in the horizontal direction? We have our tension going left, and then we have our tension going right. And the sum of these two are going to equal 0. One of them is negative because one of them is going the other direction, essentially. So that's something very important. Make sure you think about the sums here. Another thing is notice how I did not include any of the vertical forces, and that's because we're only when we do the sum of all forces here, we're only looking at the sum of forces in one particular direction. So the tension in one side is going to minus the tension on the other side is going to equal 0, which is just a very long-winded way of saying that the tension going right is going to equal the tension going left. And so since both of these have the same angle, notice how when these two tensions have the same angle, we can just cancel them out. So this means that the tension in each of the cables is going to be the same. So notice here how we actually derived that when the two angles are equal, the two tensions are going to be the same. Okay, so now if we just find one of the tensions, we can find the other one. So this is now we're going to work in the vertical direction. We've done all we can in the horizontal direction. We've exhausted our resources here. So we now need to go into our vertical direction. In a vertical direction here, what we have is the sum of all forces in the vertical direction. We want to find the sum. So again, the object is hanging, it's in static equilibrium, so it's not accelerating up or accelerating down. So the sum of all forces in the vertical direction is going to equal 0. What this means is that the force is going up, which is the tension times sine 30 for each one of these cables, minus its force going down, it's going to equal 0, which is just a long-winded way of saying that the force going up plus the force going down is equal to the force going down. So the force going up, the tensions times sine 30 is equal to the force going down. And notice here how we found previously that the two tensions are equal. So 2 tension times sine 30 equals 30. So that means that our tension is equal our force of gravity over 2 sine 30. So this is 50 times 98 is 490. 490 divided by 2 times 30 is just, means our tension should be 480. I did my math correctly. And this will be the tension in each one of these cables. Tensions are going to be identical. Okay. So that is how you find the tension in each one of these cables. So how would the tension in each cable change if its angle is only 5 degrees? So there are two ways of thinking about it. There's one way we can do it mathematically, and then there's one way we can think about it conceptually. So let's look at it both ways. So let's first look at this conceptually. It's basically, is it harder to lift something more up, or is it harder to lift something like, it's like, imagine if you were holding like a weight or something, right? You imagine if you're doing your bicep curls, trying to get yoked. It's basically, is it harder to hold it down here, or is it harder to hold it up here? Essentially? That's essentially what the question is asking. Is it harder to hold something up, or is it harder to hold something down? So, so if we do this, what we get is that if we think about this conceptually, it's a lot harder to hold something up than it is to hold something down. So what it means is that if the angle here was actually 5 degrees, these cables would have to be working pretty hard in order to keep the object up. Right? It's like, oh, it's a lot harder for these cables to keep the object up because it's fighting gravity more essentially. And so because of this, we expect the tensions to go up. We expect the tension in the rope to be higher because these two cables will have to work a lot harder to keep the object up. Okay, so we expect it to be higher. Does this check out mathematically? Well, what happened if we replace this sine 30 with a sine of 5 degrees? So before, what we had is we had 490 divided by 2 times sine 30. Now what we have is 490 divided by 2 divided by sine 5. So this time our tension here would actually be 2,811. So when we change the angle from 30 degrees to 5 degrees, we increase the tension by quite a bit. That makes sense because the tension in the cables have to work a lot harder to keep the object up. So the tension in the cables will increase if the angle is only at 5 degrees. So is it possible for the cables to be perfectly horizontal? The answer is no. No, it is not. So why is it not possible for these cables to be perfectly horizontal? Well, here's the issue. If you have these two cables that are perfectly horizontal, what is pulling the object up? These two cables now are just pulling it perfectly in a horizontal direction, but gravity is still pulling it down. So what happens is this mass is going to get dragged down until eventually these cables will sort of turn into this. So when the cables are perfectly horizontal, this setup will eventually turn into this setup. Because it's not possible for the cable to be perfectly horizontal because there has to be something that's keeping it up. Okay. Does anyone have any questions about this question? About this particular problem? Okay, so now we will step up the difficulty. Now we will step up the difficulty and look at a harder problem. Okay, so what if one of the cables is perfectly horizontal and the other one is coming in at an angle? How would we do this problem? So this weight is hanging from these two ropes, these two cables. One of them is pulling it perfectly horizontally at 30 degrees, at 30 with 30 newtons, and the other one is pulling it at sort of an angle of 40 degrees with respect to the vertical. So what is the mass of the weight? So let's take, I don't know, 8 to 10 minutes to try to figure this out. This will definitely be a little bit harder because now you have a weirder problem. Okay, so I'm going to start going through this now. We will verify if your answers are correct or not. So this problem, how do I describe this? This is one of those deceptive problems where it looks a lot harder than it actually is, I think. So let's talk about this problem first. So first off, let's draw a free body diagram as usual. We have an object. So what is pulling on the object? For starters, we have the force of gravity pulling it down. That I think is pretty standard. Make sure you always start with this force of gravity. I think sometimes people forget that gravity exists, and we don't want to do that. Unfortunately, we live in a world where gravity does exist, so forgetting it is not ideal. Let's start with the force of gravity. What else can we go next? Well, the only two things that are the only other two forces that are on this is we have a force of tension pulling it perfectly to the right, and then we have another force pulling it at an angle. So this force, and this force, pretty easy, right? They're already horizontal and vertical, pretty easy. We don't, honestly, that's nothing crazy. Now, the crazy part is when we look at this one, because this one's at an angle. So we basically want to turn this one into a horizontal or vertical force. So let's do a bit of trigonometry here.
Mr. Hu, can you make the your whiteboard screen bigger?
Yeah. But by that you mean, can you be competent on Zoom? Sorry.
A little bit.
It's okay. It's okay. Don't worry. I'm not having a rough day at all. My self-esteem is not down into the river right now. Okay. So also these pens are also killing me. They're like not great. I like having a nice pen. Okay. So now that I'm competent, and you can see what I'm doing, I think. Okay. So let's start from the beginning, I guess. So we have this weight. It's being pulled to the right. It's being pulled at an angle with force of gravity. So now we have a free body diagram. We have the force of gravity pulling it down. We have the force of tension pulling it perfectly to the right. And we have the force of tension pulling it at an angle. So I think this is not crazy so far. I think this part is going to be the more challenging part. So let's use a little bit of trigonometry here to try to break down this force of tension into a horizontal and vertical component. So this is coming at an angle. This angle is 40 degrees as given by the problem. So what we want to find this one, the x force, and this y force. So using a little bit of trigonometry, so the cosine of 40 degrees here is going to equal the adjacent over the hypotenuse. So this will equal my y over tension. And then my sine of this force is going to equal the opposite over hypotenuse. So yeah. So notice how the last problem, the x was cosine and the y was sine, and this time it's the y is cosine and the x is sine. So this is why I don't want you to memorize formulas. I think it's better just to be able to set it up and adjust your setup as possible. So this time what we did is we broke down this diagonal force into a horizontal and vertical force. Now we have a problem like this. So if we look at this problem, this actually looks a little bit easier than last time because we only have 4 forces here. And they look, honestly, like pretty nice. They look pretty nice. So this object is being perfectly hung. It's like it's not moving. It's in static equilibrium. So which once again means that all the forces are going to cancel out, which means the sum of all forces in the horizontal direction is going to equal 0. The sum of all forces in the vertical direction is going to equal 0. Because even though it has a wonky setup, right, this is still not accelerating anywhere. Okay, so this time I actually think we don't really have to. Okay, so which one do we want to start with? Do we want to start with horizontal or do we want to start with vertical direction? So which one do we want to start with? I actually we'll have to do either one, and let's start with the. Actually, does someone want to flip a coin? Okay, so here's what we do. Let's do heads. We start with horizontal, and then do tails. So does someone want to flip a coin for me real quick and tell me what they get? Because I can't decide which one we want to start with. Someone will volunteer. I don't have a coin on me right now. Let me see if I can find one.
Heads.
Heads. Okay, thank you very much. I appreciate it. Okay, so someone flipped heads. So we're going to start with horizontal first. So I think last time I sort of had a better feeling for which one we want to start with. This time we don't. I don't have a better feeling. So we just started with random. This is just to show you that sometimes even if you aren't sure where to start, just starting with one particular side randomly can get you somewhere. So we're starting horizontally. Notice how I actually didn't really know to start with horizontal this time. I just asked Galen just to flip a coin for me. So we're starting with horizontal here. So with horizontal, it means that we know that the sum of all forces in the horizontal direction is going to be equal to 0 because the ball is not accelerating to the right or accelerating to the left. So which means that the force going right is going to minus the force going left. It's going to equal 0. Which is just a long-winded way of saying that the force going left is going to equal the force going right. So we actually know the force going right, which is 30 newtons. So 30 newtons will equal my tension 2, so 40. So if we do, if we solve for tension 2, this is going to equal my 30 over c. Okay, so this gives us our second tension that we can now use to solve for force of gravity. So let's solve for our force of gravity here. So basically the same idea is the same. The force going up minus the force going down is going to equal 0. It's going to equal 0, which is just another way of saying that the force going up is going to equal the force going down. This time we know what our force is going up. This is 30 over sine 40. It's cosine 40. Well, force of gravity, which is technically 30 cotangent 40. That force of gravity. So the force of gravity is mass times gravity, which is 8. So this is solved for our mass. Finding cotangent is just, I think it's better just to go as 30 divided by tangent 40 is equal to mass times gravity. I think that's a better way of doing it. So this turn to this. So 30 divided by tan 40. H. So I got mass is 2.56. Is that what you guys got? Yes, no? Hopefully so. Okay. So let's just do a quick recap here. I just drew the diagram real quick. I drew a free body diagram of this. I decomposed the diagonal force into a horizontal and vertical force. And so now I have a better free body diagram with everything is horizontal and vertical. Then I just flipped the coin to figure out where I wanted to start with. You could start off with vertical, and then, but in which case you would have to go to horizontal, and then you have to come back to vertical. So I think in this case, I think it actually would have been better to start with horizontal, which is what we did. But I just want you to know that even if you started with vertical, and then you went to horizontal, back to vertical, you still would be ending up with the same result. So you don't necessarily know which one is better. You just have to. Okay, so that should give you our mass. I think once you pretty much have this decomposed into this free body diagram, I think the rest of it should be pretty doable. Okay, so sorry, go ahead.
I think you got the right calculation for the last step, but just may have calculated it wrong.
But I made a wrong calculation. Okay, what did you get, Chloe?
About 3.65, and I think that 30 divided by tangent 40, and then if you divide that by 9.8, you should get that. But I think the 2.56 just might be a calculator error.
Yes, I did make a calculation error. You actually, I don't know what I did, but I'm glad you pointed it out. So, yeah. So one of my other incompetencies for today. Okay, so thank you for letting me know that. That should be your correct answer, which is 3.65. Yeah. Okay. So let's do one more problem for today. I don't think we'll get to the fun assignment today, but we will get to this one. Okay, so this one is going to be, how do I describe this one? This one is going to be almost identical to the one we just did, except this time there is a block on the table, and the table has friction. Yeah. Yeah. So this one is going to be a little bit harder. This one's gonna be a little bit harder. Okay, so our goal here is to figure out the frictional force between the tabletop and the block, and to figure out the tensions in the rope. Okay, so how do I recommend starting this one? Oh, sorry, I should actually change this view so you can actually see it better. Okay, so this time what we have is we have pretty much the same setup as last time, except the horizontal cable is, instead of being attached to a wall, it's actually attached to a block. And the whole system is in static equilibrium, so it's not moving anything. And we need to figure out the tension forces, and we need to figure out the frictional force. So how would I recommend starting this? I would actually recommend drawing a free body diagram again, but for both the block and for the ball. So I would actually recommend drawing a free body diagram for both. So yeah. Let's see how much of this we can do today. Yeah, this is definitely a harder problem. Okay, so I'm gonna go through this right now and I'm gonna see how far we can get. I don't know if we'll actually be able to finish covering this one today. I might have to continue covering this next week, but let's see how far we can get. So for the most, so a lot of the problem is gonna look very similar to the last problem, except that this time instead of a wall that the second cable was attached to, we actually have a block. And this time, don't worry, you can actually see the board this time because I'm not that. Okay, so this time instead of a wall, we actually have a block here. Because I'm kind of lazy, I don't really want to redraw this that much. I'm just going to, it's just going to look flipped. Well, actually, no, because it's camera, it might even, I actually don't know if it's flipped. I actually don't know. It's mirrors, optics, whatever. Okay, so this is tension one, and this is, okay. And this is coming in at this being tested block. Okay, so so we're just going to draw two free-body diagrams here. We are going to draw a ball. It's a ball with a block. Okay, so we have a block here that's being pulled down by gravity. It's being pulled to the right, by tension, and then it's being pulled at an angle. And then we also have to draw another free-body diagram for the block here, which is going to be and so the block is going to be pulled. So my diagram, it's pulled to the. I'll do. Okay, okay. So it's being pulled to the right with tension, and then but because it's not moving, you have a frictional force resisting. So how would you do this problem? So first off, you would want to break down this tension force into horizontal and vertical components. So this Y thing, we draw a quick triangle here. The Y would be tension to sine 30, and then the X would be tension to cosine 30. So basically what's going to happen is for the ball here, you know the force of gravity because it's 8 newtons, it's given to you, and you don't know anything else. However, with the force of gravity, you can figure out their tension 2, which then you can use to figure out tension 1, which then you can use to figure out your frictional force. So basically, the general trend is using the force of gravity, you figure out your tension 2, you figure out your tension 1, and then you figure out your force of friction. Because we're out of time here, I won't actually give you the whole rundown, but this is pretty much how you do it. You use your force of gravity, you figure out your tension 2 because the ball is neither accelerating up nor is it accelerating down. So you use your force of gravity to figure out your tension 2, which you then use to figure out your tension 1, which you use to figure out your force of friction. So it is actually pretty linear, I guess. Yeah. I'll do this next week. I would say if you want to try to take a stab at it over the weekend, that's not a bad idea, because you can get a little bit of practice, but I will go over this next week. Okay, so it's 9:55 here. Okay, so you have no homework this weekend because I didn't quite get to the assignment today. I will try to cover this problem next week. So I think that should be about it, I guess. I apologize for me being really, like, I don't know, all over the place today. no matter, things happen. Yeah, that's it. So I will see you guys next week, next Monday. No homework, and I'll finish covering this problem next Monday. Yeah.
Thank you.
Thank you, Mr. Hu. Have a
Thank
good
you.
weekend.
Thank you.
Thanks, Mr. Hu.
Bye. Have a nice weekend.